it is kind of humbling at the end of a course for me to realize that I've given out like 50 bonus points for all the little typos and edits that I make, you know, and it happens in every course. So it's like, yeah, we're all fallible, you know, it happens. I just like to give bonus points when I make a mistake. So anyway, state the domain and find the derivative, right? For that first example there. We know that the limit definition is going to work. That's great news, because that again means that all the things that stemmed from that limit definition are going to, or at least they have a good chance. It's not, again, it's not a proof. It's a good indication that that there's a fighting chance that those other things are going to work too. Now you can see that there's some rules below, and we'll talk about those in a minute. But the more typical rules, those are going to be ones that you can rely upon. So we have the product rule, the quotient rule, the chain rule. Those are, you know, constant multiple rule. I think that's more of a given. But the three big ones from Calc 1, those are definitely going to be in play, right? So we start off with the domain in this question. So I'm looking at the sine function. Sine is everywhere continuous. So when you have a function that's everywhere continuous, the only way that you could end up running into trouble is if the inner function from that composite function there, the only way that you can run into an issue is if that part of it is undefined in some capacity or imaginary, right? Not the case. So I'm good on the first part. For the natural log of t minus 1, right? So let me unhighlight that and highlight that. The natural log of t minus 1, well, it's not the t minus 1 so much that's the problem as it is the natural log, right? Natural log is not always going to exist, right? It only exists for, like, you can't take log of 0, you can't take log of a negative number. So it's got to be values that are greater than 0, right? But this is the log of t minus 1. So what I would do, just kind of off on the side here, is I would just say, all right, I got my ln of t minus 1. Right, so I'll just kind of make that like a little topic, you know, a little table. So I would say that I need my t minus 1 to be greater than 0. The only way that that's going to happen, add 1 to both sides, is if the value of t is greater than a 1. All right. So that's fine, you know, because if t is, let's say 1.0001, it's still going to be a positive number. So you're good to go there. That's fine. We're good to go on the log. Now it is possible, because I've given problems where you have a log within a log, and it sounds like, oh, that's pretty mean. It's really not that bad. It's just more things you have to take into account. The tangent one is really the crispy part of this problem. All right. So we have tangent of e to the t power. Now, exponential functions are everywhere continuous. And again, unless there's an inner function of a composite that doesn't exist for some reason, you could expect that the exponential part of it is going to be fine. It's the tangent that's the problem. All right. So tangent is undefined wherever cosine is equal to 0. All right, because again, tangent is sine over cosine. All right. What I'd want to be doing is making a determination of just where this guy is equal to 0. All right. Typically, the way we handle that is by setting tangent equal to undefined. So some value, some constant over 0, but it always ends up simplifying down to just 1 over 0. So we just go that route. All right. So essentially, it's just cosine e to the t is equal to 0. That'll give us the indication of the excluded values. All right. So when I take the inverse cosine of both sides, I'd be looking at e to the t is equal to the inverse cosine of 0. All right, so I'm taking the inverse cosine of both, like I said, both sides of the equation. All right, so then it becomes a question of, all right, under what circumstances do I get a 0 when I find the cosine? That's what we were talking about before, where it's pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, and so on and so forth, forever and ever. And so what I can do, just because I'm not always lazy, but right now I am, what I can do is, oh, that was weird. I just caught a typo. Dang it. Should have been a 0. Anyway, I'll just grab this part of it. That's another benefit of digital ink. You know, I don't want to go too crazy with all the different ways in which a person can make use of this, but I would be thinking as a student, I'm like, wait, so if there's a problem on a test that's similar to a problem that we did in class, all I'd have to do is copy and paste the work that I did in class, tweak it a little bit, and I'd have my answer for the test. Sign me up. You know, so that's my way of thinking. Because like I said, it's all open notes. So, well, I didn't say it today, but that's the reality of it. So e to the t is equal to 2n plus 1 over 2 pi, where n is belonging to the set of integers. All right, but I'll just kind of forget about the set of integers for now and just focus on the e part of it, because I don't care what e is going to be equal to. I care what t is going to be equal to. Oh, I'm sorry, e to the t. I care what t is going to be equal to. So what I would do here is take either the natural log of both sides, or use the conversion to get from exponential to log form. Either way, it amounts to the same thing. So most people like applying the log, or prefer, like is a strong word, finding the log of both sides. So that's what I would do here. It's a little copy paste job. Move that a little bit. I'm gonna slide this on over right now. I'm going to throw in an ln here and an ln there, because the exponent jumps over the log like a frog. And so we get t is equal to, I could use a thinner marker there. T, because the natural log of e is equal to 1, is equal to ln of all of that stuff. Now, we would run into the issue that t also has to be bigger than a 1. All right, I'll just highlight that real quick. We got this relationship over here. I'll do that. All right, so I wouldn't want the set of integers, right? Because that would include some negative values. All right, I mean, I could use logic and create an and sentence, say this and t is greater than 1, but it's not very elegant. I mean, actually, not much of this is proving to be very elegant right now. But if we could just restrict this so that it doesn't include values of t that are less than or equal to 1, then we'd be in good shape. All right. So what I would want to do is start, I go into my Desmos calculator. I type in the natural log. I go into my functions. I got to look for it. If I don't find it, I just start typing it. I got ln, fraction 2n plus 1 over n. Oh, I'm sorry, over 2. Oops. Pi. Now that pi is contained within the natural log, so I don't want to screw that part of it up. So let me just pop it in there, and then I'll throw in a slider here.
Professor, I have a question.
Sure.
Isn't it supposed to be that t doesn't equal ln, like the slash through the equal?
Oh yeah, I'm getting there.
Okay.
Yeah. So once we make a determination of which values of n are going to lead to t values that are less than or equal to 1, then we can restrict those out of it, and everything left over would be the set of values that we do care about. All right. So anything on this end here, you can see is all going to be undefined. All right. So that we knew about going in because any negatives would just not work. All right. But then once we get to a certain point, you see we start gaining some positive ground here. An n value of 0 is still going to be less than or equal to 1, so we wouldn't want to have those, right? So those would be outside of the restriction. And so we're just looking for any values that would fail to be part of the restriction for the first piece there. All right. So I could put those. I can do what you suggested. I'll put those in there. All right. So there is that little gray area where we just got to be careful, because anything that we missed with the t greater than 1 needs to be excluded also. All right. So we're looking at it here, and we see that in this neighborhood between 0, well, really, it's in the neighborhood of from negative, in that -1 to 1 realm for n. That's when things start getting a little dicey. All right. So what we can do is we can take this function and set it equal to 0. Set it equal to 1, and make again get an idea of what that cutoff would be. Solve for the n value that'll do that for us. All right. So that's what I'm going to do here. Let me pull this up. I'm going to set it equal to 1. All right. If we convert over into exponential form, let me put the equals 1 on the other side, just so I can use the circular motion technique for converting from logs to exponential. So I'm going to rewrite. And so we'd have e to the 1 is equal to all this stuff. So e would be equal to 2n plus 1 over 2 pi. So I could divide out the pi, I can double it, so 2e over pi is equal to 2n plus 1. Subtract and then divide. So we're talking 2e over pi minus 1, and then we would multiply by 1/2, and that would get us the value of n. And that value of n would be the cutoff between what's allowable and what's not allowable. All right. So now getting that number, yeah, that's a little bit more interesting. But what I can do here is I just get a ballpark of it and just put that in for n, and then we can see. Over pi and minus 1. I think I got that. So it's about 0.36 in terms of 3.365. And you can see hopefully 0.365. You can see that that's getting you right about to the value of 1. All right. So that anything that you put in, and let me hit enter there, anything that you put in that's less than that is going to get you undefined or negative. Anything that you put in that's more than that is going to give you something that's generally okay, but you got to remember that okay is not okay. All right. So that's the big issue there. All right. So that cutoff is 0.35 for the n value, but the n value, we're only working with whole numbers anyhow. So we're looking at anything that's bigger than position 1, that n value of 1 or more. Sorry, not bigger, but bigger than or equal to 1 is going to be an excluded value. All right. So at long last, it took a while, and this is all for domains, which is eminently aggravating. But in order to get where we need to get to in terms of our understanding, the domain part of it has to be satisfied. So our domain is going to be that we're dealing with t values if I can make a t, sorry, squiggly bracket, t values such that t cannot be equal to ln of 2n plus 1 over 2 pi. All right. So that's t with a vertical line. That's our such that. Let me make that look more like a t there. All right. But then specifically, we can't have the n value be any multiple that would give us whatever I said it was, one or less. So n belongs to the set of integers, and it has to be greater than or equal to 1. All right, so it's got to be both. That's poor quality greater than or equal to symbol. So let me just move this over a little bit. I apologize. My semicolon looks like a J, but it's supposed to be a semicolon. People always ask about that. They're like, where'd that J come from? Like, sorry. All right, so all of that for the domain. You know, it is what it is, but that's part of the fun, I guess. Now you can finally actually get to the derivative. We'll draw a little line to separate. So for the derivative, just do it this way. R prime of t is going to be equal to, well, we're using chain rule here, so sine becomes cosine. But then we're multiplying by the derivative of the inner function. Derivative of t squared is 2t. All right, so we have that part. Then when I want to take the derivative of the natural log part of it, a little bit of a different story, because what we're dealing with here is a product of two functions. So I got this guy and I got this guy. So it's going to be like a little wrapping around serpentine work here, but first function, t minus 1, times the derivative of the second function, derivative of natural log, 1 over whatever is contained within the natural log, multiplied by the derivative of whatever is contained within the natural log. And it's a little late Calc 1, early Calc 2. the 1 over t minus 1 plus the second function, ln of t minus 1 times the derivative of the first function, which is just going to be a 1. All right, so that's just a ln of t minus 1. And then the tangent part of it, that's probably, well, I don't want to say the easiest, but it's as straightforward as a sine of t squared. If you know the derivative of tangent, which is secant squared, then you just go from there. So secant squared of e to the t multiplied by e to the t, because that's our inner function. All right. And this stuff here, this part of it, that's not the hard part, obviously, because you saw the amount of work that went into coming up with the domain. And, you know, there are shortcuts for finding things like domain. Sometimes it's just a simple matter of looking at a picture. Like you look at the graph and say, oh, well, it only exists from here to here to here. And you're like, oh, okay, that's really it. But in this case, you know, like you look at all we had to do for the domain, hardly anything for the actual derivative. All right. So, and it's all reliant on just basic derivative rules. So if you know your derivative rules, then you're not going to have any trouble whatsoever with the act of finding the derivative. But, you know, it's just a question of under what circumstances those derivatives are going to have meaning. Right. That's the big challenge there. Now you look at the bottom here, derivatives of combinations of vector valued functions and scalars. You're just rules. If you look at really Roman numerals 3, 4, and 5, because everything else I think is, I don't want to go too far and call everything common sense, but it's really just kind of along the lines of, well, if you know your Calc 1, the basic, you know, the most basic elements of Calc 1, then the first and second rules should be obvious. Where you look at it and say, oh yeah. If you take the derivative of a function, and then so you got your original function, and then you just take that and multiply it by a constant, your derivative is going to get multiplied by that constant too. That should be easy. All right. Also, the sum and difference rules for derivatives. So if you were to add two functions together, you take the derivative of each part and add them together separately. That's fine too. It's the product rule, which is what you're seeing here, that takes on a different form in Calc 3 because we have different ways we can take the product. It's as simple as that. All right? We have a product rule, well, I'll call it an ordinary product rule, which is not really very ordinary. It's just a little bit more consistent with the way you've always done things. All right. So that's a matter of, you know, like the first times the derivative of the second plus the second times the derivative of the first, you know, and it's like, oh, that's all good. But in a more classic sense, you're actually multiplying polynomials or two functions together. Right. For Roman numerals 4 and 5, you can see how the dot product and the cross product are getting involved. All right. But you can also see that it's still the product rule, right? Whether it's the first times the derivative of the second, or maybe you like to start with the derivative of the first function times the second function, right? In the past, it didn't matter. And for the most part, for us, it won't matter, except when you get to the cross product, right? And that's because the cross product doesn't involve the commutative property. It has the anti-commutative property, right? So it's a different animal altogether. Well, maybe not altogether, but it's got different characteristics that require a slightly different approach, right? So when I go to find the cross product between two vectors, you know, I do all the work, I come up with my answer. If I switch the order of the vectors, I'm negating the result of the cross product of the original two being multiplied. All right. So That's a little bit of a different story, right? And that comes out in the concept of the derivative also. You just got to be, it really just boils down to being careful, right? So if you're careful enough, then you're not going to run into trouble, right? So what I'll do is I'll let you explore these problems for homework, quote unquote homework, because you know the deal. Keep saying you know the deal, and I explain to you what the deal is. So you'll try those on your own, and then we'll go over those next class. All right. But what I wanted to do here is just kind of hop on over to the concept of integration. All right. It's like, whoa, limits, derivatives, and antiderivatives all in one class session. Yeah. It's really not that. It's really not that we're throwing in all these different topics in one class session. It's more like we're exploring vector value functions. Right? So what are some things that come into play when you're dealing with vector value functions or any kind of function? Well, you could talk about the functions themselves. You could talk about where the functions are approaching. You could talk about the rate of change of those functions. And you could talk about accumulated values related to those functions. So the idea of integration. All right. So we have f, g, and h are integrable, real valued functions over the closed interval a to b. It's basically telling us that the antiderivative of a vector valued function is really going to work along the same lines as the derivative work. And that is you do it a piece at a time. You do it one component at a time. All right. And whether that's an indefinite or a definite integral, it doesn't make a difference. It's still the same idea. Right. It gets a little bit more interesting when you get into the fundamental theorem of calculus, though. And not because the computations are any more difficult, but because the meaning is going to be different. Right. So it's not, like, how do you find the area under a vector? I mean, it's really not going to be the same concept in terms of the geometric applications of it as it was for integrals in x, y coordinate axes, just ordinary functions. It's going to have different meaning, but for now we're just working on the skills. All right, so what I'll do is I'll tackle a juicy one for you, and then I'll leave the rest for you to do. Right, just to show you that it's all pretty much the same, right? Conceptually. So actually, I'll do two of them. So let's look at B. So B has the three separate components, right? It's a vector valued function in three variables in three dimensions. I keep saying that. I don't know why. Never had that problem before, I swear. So I'll use this one. T e to the t squared dt plus 1 over 1 plus t squared dt plus sine of 4t dt. All right, so that's really in effect what we're finding. We're looking for the antiderivative of each part. Which is as easy or as difficult as each part presents itself as. All right, so sometimes you could use what I call it baby chain rule, but I guess it's kind of like intuitive chain rule rather than some babyish version of the chain rule. Really, it's just the idea that the antiderivative of this, and it's really just supposed to be a time saver. The antiderivative of an exponential function should involve an exponential function in some capacity, right? If I were to take the derivative of e to the t squared, it would be e to the t squared times the derivative of the t squared, right? So if I were to think, okay, well, I'm going to take the derivative of e to the x. I know that's e to the x, but if it's e to the 2x, it's going to be e to the 2x times something else. All right. So my antiderivative is going to be e to the t squared, but it's going to be modified in some capacity. All right. So what I do is just kind of off on the side or in my head, I say that the derivative of this. So just, this is me doing it in my head, because you got to get some kind of glimpse into that. All right. So if I find the derivative with respect to t of e to the t squared, what I'd be doing is rewriting the function e to the t squared, but then multiplying by the derivative of the exponent, which would be 2t, or not 2t. All right. So that would give me 2t e to the t squared, which is exactly double what I want. I don't want that 2 there. If I didn't have that 2 there, I'd have my antiderivative. So what I do is I just do a little on-the-fly correction. I multiply by 1/2, because if I had taken my derivative and multiplied it by 1/2, I can kind of backfill it in, pop in a 1/2 here. It would have canceled out and given me the thing that I was looking for, right? So yeah, you could define your u. You can say let u equal t squared and then go from there. Just kind of a waste of time. That's the thinking there, all right? So you'd have some sort of constant of integration though, because when you take the antiderivative of an indefinite integral, there's always going to be a constant of integration. But the thing is, I have 3 separate integrals here, right? For 3 separate components. So this would be the constant of integration associated with the I component. So C sub I, all right? Now, the second one is just a fact. And that is the antiderivative of 1 over, there's other ways to figure it out. You can actually figure it out with integration by parts, but it's not something that you'd want to have to do. All right. The antiderivative of 1 over 1 plus t squared is the arctangent of t. All right. So we're looking at a plus, because again, there's some integration constant involved here. I don't know what it is, and I can't assume it's going to be the same as the constant of integration for the other part. And it's also related specifically to this component of the vector. So specifically, I use specifically a lot already, C sub j, all right? So that's 2 out of 3 components. Now I just need my third component, and then we'll have it, all right? The antiderivative, I've kind of prematurely put a plus sign there, but I'll just deal with it. The antiderivative of sine under ordinary circumstances would be negative cosine, right? So that's what I'll do there, is I'll say, okay, well, I got negative cosine of 4t. So same idea as before, I got negative cosine of 4t. That's what I suspect my antiderivative is. If I take the derivative of that function, I'd be looking at sine of 4t, because negative cosine has a derivative of sine, of 4t multiplied by 4. All right? But again, I don't have a coefficient. So that means that that 4 must have gone away at some point. So I correct for that by multiplying through with a 1/4. And then I get my antiderivative, which is negative 1/4 cosine of 4t. I'll go blue here. and that's going to be plus CK. C with a subscript of K. All right. So that's actually going to be my antiderivative. However, I don't have it in the appropriate form. All right. So, oh, you know, I wrote it as a sum, and honestly, this is just my bad. So I'll take the hit on this one. It should be. I actually meant to put I, J's, and K's in there, but I kind of I deked myself here. So let me just kind of tuck it in here. Oh man, I cannot write. So those should have been there all along. Apologies for that. Which means this would be an I. The I component, that's not an I. I started almost writing a K, then I settled on a J. Eventually I get there. And so this one would be the J component. I'll bring it back out in a sec. And so that would be my antiderivative. Yeah, you could write it in component form if you want to. There's no requirement that you do one way or the other, or at least I'll never require you to do it one way or the other. So that's entirely up to you. Just you know, learn from my mistakes. Once you go down one path, you know, you got to kind of stick to the notation that you decide upon. So once I decided to go IJK, I needed to actually stick with it, and I failed to do that. But you know, you get there eventually. That's the whole point. Okay. So then one more problem. Part C. So this one, we're dealing with the cross product in the antiderivative context. So there's a couple of ways to handle it. One way, I suppose, would be just try to guess your way through it. That's not really a good way. The real way to do it would actually be to find the cross product and then integrate. Right. So there's a little bit more work involved here. Now, technology, there are technological resources that you can use in order to get this result, but that's kind of beyond what we're working on here. So at least for now. So what we're going to do is we're going to compute the cross product. I'll just kind of jot it down over here. I'm going to try to maximize the space I have here. So we have t squared, and t cubed. And then t cubed, t squared, and t. Now this should boil down to something multiplied by unit vector I minus something times the unit vector j plus something times the unit vector k. Now those somethings are dependent on the 2x2 square matrices that we're coming up with from the vector that we're, I'm sorry, overusing vector, from the 3x3 square matrix that we're finding the cofactors for. All right, so I'll use some strategic highlighting here. I wanted that to look like a rectangle. So we have t squared, t cubed, t squared, and t. For the j, that's the weird one where we're just ignoring the j column. So I'll just kind of do it as sort of like a u here. If it lets me, it kind of let me. All right, I'm not gonna mess around with that. I'll just live with it. T cubed, another t cubed, and a t. And let me get a blue here. Oh, I already got blue. I got some kind of blue. Let me get go light green for those keeping score home. For the k, that's t cubed, t cubed, and t. All right. So then it's diagonal down minus diagonal up. So t cubed.
Professor?
Yeah.
Isn't that t squared, t cubed, t squared?
Oh,
Okay.
yeah, yeah. Yes, thank you. I was looking at the wrong thing. So t squared, t cubed, t squared. Thank you. Very good. Thank you, thank you. All right. Might as well double check everything else while I'm here. Yeah, I think for whatever reason, I just accidentally rewrote the j again. I don't know. So t cubed minus t to the fifth, that's my I, minus t squared minus t to the sixth, that's my j, plus t cubed minus t to the fifth, that's my k. So, you don't want to rest on your laurels here, because now we're at the point where we could actually start the process of answering the question, right? Because it's said to find the antiderivative of that, right? So what I can do is just kind of tuck in a little integration symbol here. Let me, well, I guess I could tuck it in, but let me not be too lazy. I'm going to rewrite, or I'm going to copy paste it, then I'm going to tuck it in. Let me resize a little bit. All right. So then you can see here that this is going to be much easier than the previous one, because it's just the reverse of the power rule. There's nothing really fancy going on with this one, right? In terms of the quality of the antiderivative. But we're kind of due for a break, so why not? So we're looking at, for the i's, 1/4 t to the fourth minus 1/6 t to the sixth minus, let's not get too crazy. We need the integration constant, so plus I cannot make a plus for some reason. C sub I, that's my I component. Then plus, minus 1/3 t cubed minus 1/7 t to the seventh. That's my j limiting integration constant, so C sub j component. And then plus, this time it really is a plus, 1/4 t to the fourth minus 1/6 t to the sixth. I'm going to have to shrink a little bit, shrink a dinky. So that's going to be plus C sub k. And that's my k coefficient. All right. So, no, it's writing. Writing's for nerds. No, it's fine. We can get it done. It's not ideal, but ideal is not the right word. It's really not what you have in mind. You don't want to have to do this, but in terms of intense thinking and problem solving and stuff like that, that's not what we're dealing with here. This isn't really that complicated. It's just you got to do the work. All right. So, that's part of the fun, I guess. Just kind of navigating yourself around the different types of problems and how they kind of manifest themselves and what the expectations are and all that good stuff. I belatedly decided to. I'm sorry if I'm throwing people for a loop here. I just realized belatedly that it's probably going to make more sense if I write it like this. All right. So, it's still your basic integration rules. It's still not the complicated stuff, but it still is going to require you to do some writing and working and thinking and putting forth effort, et cetera, et cetera. All right. So that's part of the fun, I suppose. Everything, I guess, is part of the fun. Yeah. All right. So that's where we're going to leave it for tonight. Yeah, because the next topic is a little on the beefy side. So we got to cross that bridge next class. All right. So putting stars on A and D. We'll grab those problems next class, and then we'll go from there. All right. So let me stop the recording.